Today we're going to talk about two new types of series and how to tell whether they are convergent or divergent. Last class we talked about what was called the nth term test, which is when you take the limit as n approaches infinity of the equation and see if it approaches a number. If it approaches a number, it converges. If it doesn't, it diverges. Okay? Today we're going to talk about two special types of series, a geometric series and what is called a p-class series. So let's start with geometric. This is something you were quickly introduced to in Algebra 2. It is a series where things increase by multiplying each term by a common ratio. So it says in the box here that a geometric series is in the form of the sum from n equals 0 to infinity of a times r to the n. So in other words, you start with a term a, then you multiply that a times r, then you multiply a times r times another r, and then a times r times another r, and that's where they're getting this. Does that make sense? Every time we're multiplying by one more r. This is just a, and then it's one more r, then it's two r's, then it's three r's, and then up to n r's. As long as a does not equal 0. Now what would happen if a was 0? It would just be 0. It would be boring sequence, boring series. The constant r is called the ratio, and that's very important because that is the determining factor as to whether or not this thing is going to converge or diverge. Okay? So here's the rule. If the absolute value of r is greater than 1, the series will diverge. But more important, well, I think is more importantly, we want to know when it converges. It converges when the absolute value of r is less than 1. But in more simple terms, if r is between -1 and 1, that's how you know it converges. If r is between -1 and +1. Now, not only can we tell if it converges or not, just like the telescoping, we can actually figure out what it converges to. The way you find what it converges to is once you know it does converge, the formula is right here. The formula for a geometric series' sum is a, which is the first term, divided by 1 minus r. So if you add up all the terms of an infinite converging geometric series, that's what it will add up to be. Okay? Other than the telescoping series, the geometric is the only series that has this characteristic. Not only can we determine whether or not it converges, we can actually find out what it converges to. Okay? With telescoping, that's one where all the terms canceled out and we ended up with the first and the last. Okay? And we knew what the answer was going to be. This is the same thing. So it's very important that when you do these, you recognize, number one, that it is geometric, what r is, and then determine from there whether it converges or diverges, and if so, what to. So let's take a look at number 1. It says expand the series out 4 terms and then determine whether it converges. If it does, find the sum. So let's work this out. Notice this starts with n equals 0. So if you plug a 0 in for n, what is that going to be? 1. Plus, now plug a 1 in for n. What are you going to get? 2/3 plus 4/9 plus 2 to the third, 8 over 27 plus ... It goes on forever. But those are the first 4 terms. Okay? Are those fractions getting smaller? Do they look to be? Yes. Yeah, they look to be. So chances are it may converge. What is r? What am I multiplying by every time to get from one term to the next? 2/3. 2/3, exactly. r is 2/3. Now, after you find r, ask yourself, is r between -1 and +1? Yes. Yes, therefore it's going to converge. Therefore, it converges by the geometric, which I'm going to abbreviate, series test, and you have to write this every time, and the sum we're going to actually calculate as well. You can only calculate the sum if it converges. You could plug the things in if it diverges, but it's not the right answer. Divergent means it doesn't have a sum. Convergent means it does. So now we're going to use the formula up there, which is A, the first term, 1, over 1 minus R, 2/3. And we're going to, without a calculator, clean that up. So what is 1 minus 2/3? 1/3. And that is 3. So if you add up 1 plus 2/3 plus 4/9 plus 8/27 and keep going and going and going and going and going, this sum will eventually be 3. Questions? Yes?
So what if the R wasn't literally -1?
Then it would diverge, and you just say that the series diverges. Yes.
And so if it diverges, do we not have to do the summation part?
No, because there is no sum. There is no answer. The whole meaning of divergent means the terms do not add up to a specific value. Okay? All right, try number 2. So plugging in 0 to the number 2 equation, what is the first term going to be? 1. And then what? 3 halves. And then 9/4 and 27/18 plus dot dot. Basically all the fractions from the first problem turned upside down. Okay? Are those fractions getting bigger? Well, 3 halves is 1.5.
No, they're getting,
Question?
Why is it 27/18?
Yeah, but
Because I did that wrong. What should it be?
87.
27/8. I don't know why I thought it was 18. I was just making sure you were paying attention. That's a teacher's perfect answer for stuff like that. Just making sure you were paying attention. Okay, thank you. All right, so it's the same thing as the previous ones. Now, back to the question, are they getting bigger? Yes. So, thinking they might be divergent. Okay, what is R? 3 halves. You multiply by 3 halves to get this and 3 halves to get that, so R equals 3 halves. Therefore, is R between -1 and 1? No, it's too big. Therefore, it diverges by the geometric series test. It diverges by the geometric series test, and you stop right there. It's just going to get infinitely large the more you add on fractions. There is no sum. Are we good? Okay, I'm not going to do all of these because you don't need it. Let's go to number 5, however, because number 5 is a negative in it. Let's see what that does. The formula is 8 times -3/4 to the n. So we're going to plug in 0 first. What is 0 going to do to just the fraction part? It's 1. So the first term is 8. Plus, now plugging the 1 into the -3/4 is -3/4, right? Think of 8 as 8 over 1. So that would be -24 over 4. Agreed? Now, I know that's -6. You don't have to reduce it. You can just leave it like that. And actually, it makes things easier if you don't, because you can see the pattern faster. Okay? So the next one, plus, when I square this, what's going to happen? It's going to be positive. So it's going to be 9 on top, times 8 is 72, and then over 16. Very good. What sign will the next term be? Negative. Very good. So -3 to the third is -27 times 8. Let me just tell you it's -216 over 4 to the third, 64. Now, these are going back and forth and back and forth. But if something, it is oscillating, but they're oscillating and possibly getting closer together. So if something oscillates and it gets closer together, could it converge? Mm-hmm. Theoretically, yes. So the determining factor is R. What are we multiplying by every time? -3/4. Are you seeing where R is in the formula? Mm-hmm. It's just right there. Whatever the n has the power of n, that's R. So is this one going to converge or diverge? Converge. Therefore, it converges by the geometric series test. And the sum will be, because I can find it, okay, you do the math on this one. So all of those terms, the positives and negatives will kind of cancel each other out. And eventually get closer and closer to 32 over 7, which is about 4.28, 4.5, about 4.5. Okay. So now I want to do one more, because one of these at the bottom doesn't look like those others. It doesn't give you the formula. So what you have to do differently is, instead of you having to write out the terms, which they already did, you don't have to write the sigma. You just have to tell me what R is, because R is the whatever determines if it converges or diverges. Now, what is R?
1/2.
Okay, how did you get that? It's decreasing by 1/2 every time. Another way, if it's not as obvious as that, it's the second term divided by the first term. That always works, okay? So R equals 1/2 in this case. Is it going to converge?
Mm-hmm.
Yes. Therefore, it converges by the geometric series test. So the sum will be A1, which is 4, over 1 minus 1/2, which is 4 over 1/2, which is 8. All right. I did this in first period, and I'll do it with y'all too if it's necessary. Does it bother any of you that 4 divided by 1/2 is 8? Does that just sound wrong? Yes? Okay. Now let me show you a way that I thought was really cool that somebody showed me once on how to do this. Okay? Look at this. So back in the days when you first started learning division, they would give you a certain number of items and they would say group them. 12 divided by 3. How would you do, or actually let's do 12 divided by 4. I have 12 sticks. I want to divide it into 4 groups. You circle them. And how many are in each group? Be 3, right? So 12 divided by 4 into 3 groups. Okay, 3 per group. Now, if you were going to divide 4, let's make these longer, by 1/2, that means I want 1/2 a stick in each group. I want 1/2 a stick in each group. How many groups am I going to have? 8. That's where the 8 comes from. It's an interesting way to think about it, but that's exactly why 4 divided by 1/2 is 8. Okay? Little side note there. Any questions about the geometric series? Pretty easy, right? Okay, turn it over on the back, please. To the back, to the back. Now, the third special form, telescoping was the first, geometric was the second, P-series is the third. A P-series is in this form, n equals 1 to infinity of 1 over n to the P. So 1 to a power, 2 to a power, 3 to a power, 4 to the power. Powers have to be the same, okay? Here's the way it works. A P-series converges if P is greater than 1. And it diverges if, I want you to mark this out and change it, if P is less than or equal to 1. That's the way it is in the flip book, and it's actually, it's true both ways. But if P was negative, when you see something on the bottom of a fraction that has a negative exponent, where do you put it? On the top. So if I move something like n squared, n to the negative 2 that's on the bottom to the top, it'd be n squared. Now think about it. 1 squared plus 2 squared plus 3 squared plus 4 squared. Isn't that just getting bigger and bigger and bigger? Yes. So negative exponents will also diverge. So a P-series diverges if P is less than or equal to 1. So let's take a look at this one. What you have to figure out with a P-series is what the exponent is, because that's the key. I'm not multiplying by the same number every time anymore. So what is the power on each one of these? It's 2. So this is 1 over 1 squared. This is 1 over 2 squared. Then 1 over 3 squared, 1 over 4 squared, and so on. Do you agree with me?
Yeah.
Okay, what is P? What number is P? 2. So, like the other ones, you have to identify the constant that makes the difference. In this case, it's P equals 2. Is it going to converge or diverge? It converges if P is greater than 1. Therefore, it converges by the P series test. That's what you write. Yes, ma'am.
So P just means exponent, right?
P in this case is the exponent. Yes, ma'am. So if you notice that on a sequence or on a series that the exponents are the same every time, notice that the n is what term it is. Okay? First term, second term, third term, fourth term. N is what term it is. P is its exponent. All right? The next one. What's the exponent? This is 1 over 2 to the 1/2, right? This is 1 over 3 to the 1/2. This is 1 over 4 to the 1/2. Does that work for the first one? Is 1 to the 1/2 1?
Yes.
Yeah. Okay. So P here is 1/2. Does it converge or diverge? It diverges. Therefore, it diverges by the P series test. Period. Okay. Very simple. Find the exponent, determine whether it converges or diverges. With R, smaller is better. With P, bigger is better. Okay? All right. Any questions about P series so far? Okay. When P equals 1, it makes a special kind of series, and that's what it's talking about here. The series 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 can be written as this one, which is a P series. P equals 1. Is it going to converge or diverge if P equals 1? Exactly. It diverges, okay? By the rule above, it diverges. This is called the harmonic series. It's a special kind of P series, and it's called the harmonic series. Okay? Now, where have you heard the phrase harmonic as part of another word?
Harmonica.
A harmonica. A harmonica is based on the harmonic series. A harmonic series is how guitar strings are constructed and how frets are made on a guitar. I don't know all the details, but it has something to do with it. Okay? A general harmonic series is in this format. Notice here, it's 1 over an to the first plus b. And it does diverge because it's harmonic. In music strings of the same material, diameter, and tension, whose lengths form a harmonic series, they produce harmonic, which is pleasing to the ear, tone. Another word is harmony. Harmony sounds really good if it's done right. Agreed? The tones are based on the harmonic series. Okay? Now, I'm going to skip this part here and I want to go to the bottom, which I think this is just kind of an interesting little fact here. It says, suppose we stack identical books of length 1, just say a whole stack of books of all the same size, so that the top book overhangs the book below it by half. So half of the book is overhanging. And then the next one is overhanging by just a quarter. And the next one's overhanging by 1/6. This happens to be harmonic, it's 1/2 times the harmonic sequence. Now, if I could make an infinite stack, would that stack ever fall over? The answer is no.
What?
It would not fall over.
Wait. Do you mean going down or going up?
The top one is out the farthest.
Wouldn't the top book fall?
Mm-mm. The way it's built, just because of the way the harmonic series works, each one that you go down has such a little bit amount sticking out that it gives it enough balance to where it would stay. This is called the Leaning Tower of Lyre. It will just barely balance, just barely. I'd have to go look up the math on this, and it talks about it. It takes 31 books for the overhang to be 2 books long, 227 to be 3 books long, and over 272 million books for the overhang to be 10 books long. And it says you can try it with a deck of cards and see if you can get it. But you'd have to be measuring accordingly. If you've ever taken a deck of cards sitting right here and you just kind of slide the top out so it's kind of overhanging a little bit, that's kind of the same idea, because you can slide it out quite a ways and it won't fall. Okay? So that's what they're talking about here. Harmonic series have a lot of interesting applications in the real world. They really do. Okay? But just remember today we have the geometric, the p-series, and the harmonic that we're going to use. All right, now in the flip chart, if you would turn to the page where we glued the stuff on today, the geometric p-series harmonic page, wherever you have the geometric one, look at that first. This is kind of a summary of everything that we've done so far. Okay, the conditions have to be, it has to be in the form of one of these two. Now take a look at these two sigmas on the end. How are they different?
The 0.
One starts at 0, one starts at 1. And the exponent changes accordingly, because if you plug in 0 to this one, you're going to get r to the 0. And if you plug 1 into this one, you're going to get r to the 0. So there's the same thing, just written slightly different. As long as they have a r in there, it is a geometric series. So look for this format. A number times another number to a power of n. And remember, if absolute value of r is greater than or equal to 1, it diverges. If the absolute value of r is less than 1, or you may want to add -1 is less than r is less than 1. I think I'm going to do that myself. So you may want to put this underneath here. -1 is less than r is less than 1. That's the most often thought about way of doing it. R is between -1 and 1. The series converges to the sum s equals a1 over 1 minus r. And this is how you write it. The series converges to this, or that it diverges by the geometric series test. And that's basically what we did. We put the sum at the end. It doesn't matter. It doesn't matter. A lot of times they don't care what the sum is, just the fact that it converges. Okay? Now, p-series test. P-series test is at the top of my page. Now remember that a p-series is a series that looks like this. 1 over n to the p power. It converges if p is greater than 1, diverges if p is less than or equal to 1. And so you write that the series converges or diverges by the p-series test. Now, we talked also about harmonic, and I don't have a page for that, so we're going to write it in. Now, I'm writing it on the p-series page because it is a p-series. It's just a special type of p-series. So write harmonic series. Now, you can call it either one. You can call it harmonic, or you can just call it a p-series. It is n equals 1 to infinity of 1 over n. N equals 1 to infinity, the sum of 1 over n, which happens to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot, dot, dot. It goes on forever. Now, this is one of those weird instances where even though the fractions are getting smaller, it still diverges. And if you look back on the notes page, there was a whole proof there as to why it diverges. Okay? Now, the other thing we're going to write is the general form for the harmonic, because sometimes you will see series this way. N equals 1 to infinity of 1 over a n plus b. As long as n is to the first power, that is going to be a form of a harmonic, and both of these always diverge. Always diverge. I'm going to put a S on the end because this always diverges. That looks better.
Is
Okay.
that like a times n?
A times n plus b, like mx plus b kind of thing. Okay? So in today's worksheet, you're going to be looking specifically for geometric or p-series patterns. And then you're going to say whether it converges or diverges based on the test. Make sure you identify what is p, what is r, based on the formula that it fits. Okay? Do you have any questions for me? Yes?
Just one more question about where it says always diverges. So when you say that it always diverges, are you talking about, because this is dealing with p-series, so you're talking about in the event that the p is greater than 1?
If the p is less than or equal to 1, this is the equal to 1. The harmonic is the equal to 1, and it does diverge by this rule up here. it says diverges if P is equal to 1.
But you're saying that if we ever have to use general, the general form,
Yeah.
it's always the.
It's always a divergent, even though it's got that B added on the end, it's still divergent. That's the point. All harmonic series of any kind are divergent. Okay, anybody else? All right, we're done.